Ma'am, till we start, can we
Yeah.
ask general questions which like doubts I had from?
Yeah. We can do it in that mode also. So uh, okay, let's start the session, and let's start with the question answer round. So I'll be putting up the video recordings of these classes also. So I just started the recording. So you may ask your question now. Okay.
Ma'am, I had doubt in the second lecture in which ma'am mentions
Mm-hmm.
about non-linear analysis.
Mm-hmm. Yes.
I have never done that, so how is non-linear analysis done?
See, do you understand what a linear analysis is?
Yes, I do understand what is linear analysis.
So the material remains. See, linearity can be in the terms of the material as well as in terms of the geometry of the structure as well. So let's say you have to study when you write down the equilibrium equation of a uh, of a uh, of a column, let's say, so
Mm-hmm.
or of a beam, let's say. So do you write it like in the undergraduate level? We always write it in the equilibrium, in the initial state before it has deformed. So that is a part of the linear analysis where the geometrical nonlinearity is not brought into picture. Or uh, if I give an easier example, it can be, just admit everyone. Yeah. Or if you can say the material is linear, or you can say it is obeying uh, Hooke's law. So if the material behaves, suppose it's the member which you are studying, it's made up of steel, and it behaves, it has a behavior like this. On this axis I have stress, on this axis I have strain, and my material will follow this behavior. Then you are stepping into the arena of nonlinear analysis.
Hmm.
So it is an advanced method of you can say an advanced course of nonlinear analysis. And in this course you'll be exposed to that as well. Like, initially we are studying only linear systems, and then we study nonlinear systems as well. And if not in this course, you can look at some other courses on NPTEL as well, where uh, how do we do such kind of analysis is explained.
Okay.
Yeah.
Ma'am, one more thing.
Hmm.
Does small deformation theory, I mean, is it synonymous to linear analysis and large deformation theory synonymous to nonlinear analysis?
It's not uh, it's one of the assumption, like the terms which you use, small deformation and large deformation, is what I was telling, that when you write down an equilibrium equation in a linear analysis, you write down it in the initial state itself. Like if there is a column, and you are applying a load like this, and if this is, let's say, a small deformation problem, if you write down the equilibrium equation, it will be something like this. Like, I should have removed the support and then put this reaction. Let's assume this is the equilibrium, the free body diagram for this column. But
Okay.
actually what will happen if I write down the equilibrium, I want to write down the equilibrium equation in a deformed configuration. What will happen? The column will buckle slightly. Suppose I perturbed it, that is, pushed that this slightly, so that I study its stability. You might have done this while studying
Yes.
Euler Bernoulli, the column, while establishing the buckling load. Then in this situation, if I just put this P load, then will this column, is this column under equilibrium? Is it balanced? No, because I'll have a, let's say, if this
Moment over
is
the
delta, there will be a moment established P delta in this direction. So I will have a force, let's say, If the length of the column is h, so I will have some,
pH.
yeah, I will have a column like this. Is it? No. In this way. The my point is, you can figure out this. There will be a horizontal force in this system. Let's say you can put down the values properly. So this the figure on the right hand side, this is you're writing down the equilibrium in a deformed configuration. So the large deformation term is used in this context. So what you're thinking is kind of correct.
Okay.
Hmm. Any other question? The floor is open. If anyone else also wants to ask some questions, you can ask. So the entire motive of the session is you go through the lectures and you ask questions, or uh, I'll try to pose a problem, and through that problem, we'll try to understand the concept which was there in the class. Like, this is the mode which I'll try to follow today. If you have any suggestions at the end of the class, you can suggest, so that we can incorporate it in the next class. Okay, then I'll pose a problem and then we'll try to solve the question. So I'll briefly introduce myself. I am Sukanya Karmakar. I'm a fourth year PhD student at IIT Kanpur in structural engineering. My core domain is earthquake engineering. I'll give my email ID. My email ID is, if uh, like beyond this class, if you have any doubt in the subject which is not clear, you can mail me. I'll be happy to help you. So, in this way, both of us grow. So, okay, let's start with some question answers thing, because ma'am had covered uh, a lot of theory in the class. So, first, we'll uh, start with some problems where we'll want to write the equation of motion. So I hope my voice is clear, my screen is visible, everything is fine.
Yes, ma'am.
Okay, okay. So let's say I have a pendulum, and so this is question number one. So you have to derive the equation governing the free motion of a simple pendulum. The pendulum is initially at this position. Its length is L. I move it up here. The mass is M. Let's assume that the string is inextensible, meaning the length of the string does not change. This length remains L. I move it by theta. So uh, it there this is a single degree of freedom system. How do I tell it's a single degree of freedom system? All the mass in the system is concentrated at this point, mass M. So I want you to write down the governing free motion equation of a simple pendulum. And what are the assumptions? The assumption is point mass m is suspended by a light spring. Why light spring? Because I want it to be weightless. Of See, nothing can be weightless, but its weight in comparison to that ball will be very small. So uh, let's briefly stop for about 2 minutes. I want you to first try this, and then we'll discuss. So I'll give you a hint. Just cut this string here and try to write down, or try to draw the free body diagram for this ball. This is your hint. I request everyone to uh, try to solve this. Okay, let's discuss the solution. This is the ball. This is the string. There will be a, a string can carry only tensile forces. Under compression, the spring will slack and not carry any force. So this force has to be tensile in nature. Then the weight of the ball, it will act in the vertically downward direction. And in this tangential direction, here let's use the D'Alembert's principle, where you have to apply an inertial force uh, opposite to the direction of the uh, unbalanced force. So this body is accelerating in this direction. So I apply inertial force in this direction. Let me call this Fi. And let's say this is the support. Let me name this point O. Now, what is the value of this inertial force? From our knowledge of circular motion, we know that this is equal to uh, ml theta double dot. Right? Now, let's take the moment about this point O. Then I'm writing the moment equilibrium equation. So that will be, so I am doing summation of moments about point O. And let's take clockwise moment to be positive. So Fi into this distance is L, okay. Then T will not have any component because it is passing through point O. plus mg when it's about this. So this angle is theta. So this distance is L sine theta. So when you're taking the moment of the force mg, it will be the force into the lever arm, that is L sine theta is equal to 0. Now just substitute this m L square theta double dot plus m g L sine theta is equal to 0. So this is the uh, equation of motion of a simple pendulum for free motion. Like why free? You first, no force is acting on the system. You give an initial condition, that is you rotate the system by an angle theta, and then you leave it, and then it undergoes this motion. So what we see here is a it's a non-linear differential equation. How did I tell it's a non-linear in theta? Because if you know the expansion of theta, it's a series where there are terms where the theta is there in it can be in the power of 2, 3. Uh, it's basically related to the expansion of sine. So this is a non-linear differential equation in theta. So here, if we assume that theta is extremely small, then we can write that sine theta is approximately equal to theta. So this equation can be made a linear equation, and we can solve this, right? So this is the equation of motion. Yes, you may unmute yourself and ask your question.
Ma'am, could you explain how the inertial force is ml second derivative of theta?
Yeah. So we know that uh, force is mass into acceleration. So m omega square. It's in this direction, but I'll have to look at that exact terms. Maybe at the end of the class, by that time I'll figure out and I'll inform you.
Okay, ma'am.
Okay.
And
Yeah.
in the equation
Mm-hmm.
is non-linear. You are saying because of that sine
Sine
theta,
theta. Yeah.
when it is converted using Taylor series, so then it will have multiple terms.
Yeah. Yeah.
Oh,
Yeah.
okay.
Right. Okay. We'll take up this question at last. This I'll remember. Okay. So okay. I hope this is clear. Simple. Write down. Drawing the free body diagram and writing the uh, what we do in statics itself. Like using the LMS principle, we are converting a dynamics problem to a statics problem. So this is what was already discussed in the class, that you have a body of mass m, then suppose I have both a spring which is giving the resistance, if I say, uh, and you have a damping source as well, and it should not float in the air, and let's say this is the degree of freedom u with which you are uh, describing the system, and I pull it by a force of pt. So this is straightforward. When you write down, establish the free body diagram, this is pt, Then since you are putting it like pulling the system in the rightward direction, you have resistance, so Ku and Cu dot, and you will also have mass acting here. The weight will act in the downward direction, but there will also be a normal reaction. So you're not interested in the vertical equilibrium is there, so we are not concerned about it. And if I use the D'Alembert's principle, you will have the inertial force, which is mu double dot mass into the acceleration. And if I write down the equation of motion, it will be, let's say terms on the right hand side are positive. Pt is equal to mu double dot plus cu dot plus ku is equal to p of t. Okay. Now I'll give you a system. The system is like this. This is what we had seen in the class. So now I am giving you a system that you have a single story frame. All the mass in this frame is lumped at this point. Okay. The frame is this beam is rigid. So this U is uh, the only degree of freedom. It's a single degree of freedom system. That is, this U is able to describe the displaced position of this system. It's an independent degree of freedom. So, and you are applying a force P of t at this level. I want you to develop the equation of motion for this system. And you have the stiffness, let's say the total stiffness provided in this frame will be because of the two columns, and let's say the equivalent stiffness is K. Okay. And you also have a damper like this, and its coefficient is C. I want you to write the equation of motion for this single story frame. Try to think on the lines of what we did just in this example, which was done in the class. You have to write down uh, the you have to draw the free body diagram of this mass. So try, please attempt it. I'll wait for 2 minutes and then we'll discuss it.
Ma'am,
Hmm.
is it a rigid frame?
This beam is rigid.
Okay, beam is rigid,
Like
but still.
when I
Mhm.
pull it, it will deform like this. If I draw the deformed shape, maybe it will help you. By that, I mean the amount by which it will move here. Let's say
Mhm.
delta x, it is same here, right?
Okay,
The length of the beam does not change.
but the columns can be compressed. So, will it be 2 degree of freedom problem or 1 degree of freedom?
Why will call
I
in
mean, the vertical
dynamics?
member.
No, no. See, the columns are actually inextensible. This is one more assumption.
Okay.
It won't be compressed. Okay. So what I want to do is I'll cut the frame here and write down the diagram for of the portion of the beam of this portion, the portion on the top of this portion. So okay, apart from this, what other forces will appear? What do you think?
One term would be C into U dot.
Yeah, so let's say, yeah, so C into U dot or FD, the force due to damping. Let's call this, where FD is C into U dot. Any other force?
Due to D'Alembert's principle, we'll have
Yeah.
inertia.
In which direction would it be?
Opposite to force.
Okay, that is in this direction. You will have Fi. Okay, this is one force. And what will its value be?
Mass into U double dot.
Yes, and there will be uh, one more force from the columns because they will provide lateral stiffness, right? And
Okay.
I am telling that the equivalent stiffness is K. So we know if we know the stiffness forces K into
Deformation.
deformation. So this will be, let's say I call it Fs. Fs is K into U. Now I can write down the equilibrium equation of this mass in the horizontal direction. It will be Fi plus Fd plus Fs is equal to P of T. And if I substitute is Mu double dot plus Cu dot plus Ku is equal to P of T. So you can see we get the same equation for it. The systems look different. This system, the mass spring dashpot system, and the system where you have a portal frame with certain assumptions that uh, entire mass is lumped at a point uh, in the slab. Let's say here it's lumped at one point. The beam is rigid. The columns are actually inextensible, and we know the equivalent stiffness of the system K and the damping coefficient is C. These are like we can study how would we figure out this K. Maybe I'll do that example as well. So we see that the spring dashpot mass system behaves. The equation of motion is quite similar to that of this plane frame. So any questions on this? Okay. So one more small question again in this topic. So you have a bar like this, and you have a rotational, like till date, whatever springs you were seeing, those were linear springs. Like uh, in that, how do you write the force in a spring K into U? where U is the deformation, actual deformation in the spring. So what I'm drawing here is a rotational spring. In a rotational spring, you will have a stiffness, you can call it a rotational stiffness into the deformation. Here, deformation will be theta, the rotation happening in the spring. That is equal to the force which the spring will provide. So the spring has a stiffness K. So something like this. Then you have it has a weight W, and this length is L. Okay. So the system consists of a weight W attached to a rigid massless bar of length L. So again, this is a rigid massless bar of length L. Weight is W, I've already given, and it is joined to a spot by a rotational spring of stiffness K. We have to derive the equation of motion and assume first that the deflections are small. That is, when you like move it to this position, just assume that this my drawing is very bad. Assume that the deflections are small. Assume smaller deflections and n- uh, neglect the rotational inertia of the mass. Neglect rotational inertia of the weight and yeah, first write down the equation of motion. Okay. Try solving this question.
Rotational stiffness is force upon rotational deformation.
Yes.
Okay. That means force upon theta.
Yes.
Okay.
Okay. So let's try this question. So this was one of the doubt asked by one of the students, that how did I write this inertial force? So we know that acceleration in a circular path is acceleration is v square by r. And so the rotational in terms of rotational coordinate, it is omega square. V is omega square into r square by. Okay, just I was trying to explain this because you need this uh, thing here. So F I is equal to m l d atom. Okay, let's not mess up things now. Just concentrate on this question.
Ma'am, I agree till omega square r square, but how is that getting
Yeah,
converted?
yeah, yeah, yeah. True. Uh, my screen just got disconnect. I'll first fix that. Yeah, I agree with what you're telling. Okay, my uh, tablet just got discharged, so this will get switched on. Or you can keep trying the question as you want. We'll resume the class. Yeah, you are in the correct direction. Okay, my mic is connected. So sorry for the trouble. I forgot to charge my tablet. So we were here. How is this inertial force ml theta double dot? So what's basically theta? So theta is the motion in the radial direction. We can tell that it is u, or like the way we were handling u earlier. Fine. Now, what is where is my pen? Yeah. So, what is the velocity? Velocity is omega into r. What is r here? R is equal to L. And omega, what is the radial velocity? Radial velocity will just be the change in this rotation. So theta dot. And what is acceleration? Acceleration is v square by r. So it will be, or instead of writing like this, I think so. This is a more convincing manner. Change in velocity with respect to time is acceleration. So change in uh, theta dot is theta double dot, and force is mass into acceleration. So I think so. This treatment is more elegant rather than being prepared. From there also, I'm making certain mistake. That is why I'm not getting. I'll tell you, but this is what I could think of. So
Yes, ma'am. Thank you, ma'am.
yeah. So let's get back to this question. So here, uh, could you draw the free body diagram and identify the forces? Similar, the only change is earlier we had a linear spring and here you have a rotational spring. So, uh, so let's say you have a bar like this, and let's say this support is O, and from the vertical, this angle is theta, right? And at this point, you have the mass. Let's say this is W. Here you have the weight sitting. Fine. What are the other forces? One will be the spring force. Now you are rotating the body like this. So the spring will try to restore it. So it will be, the restoring force will be in the anti-clockwise direction. So this is Fs. Right. One more force will be, we are using the D'Alembert's principle. So I'll have the inertial force as well. So if this is the path of the body, we will have an inertial force like this in the tangential direction. Let me call this Fi. Then what is this Fs? As we just discussed, it will be k into theta. And what will be this Fi? We just discussed it. It will be ml theta double dot. And since in this question you are dealing with the weight term, so W by G L theta double dot. Then what will you do? Similar to pendulum question, let's take the moment about this point O. So summation of moment about point O is 0. And let's take anti-clockwise direction to be possible. So Fi at the direction distance L in the anti-clockwise direction plus Fs is equal to, you have this acting at a distance of,
L sin theta.
yeah, so it will be uh, W I want to write in the form of WL sine. Fine. Then you can just substitute these terms and get the equation. Like for the sake of completion, let's do it. W by G L square theta double dot plus A into theta plus WL sine theta. And let's assume that this is a small deformation problem, that theta is extremely small. So let's write sine theta is approximately equal to theta, assuming small rotation. So you can write W by G L square theta double dot plus K theta to WL into theta. And I can just simplify this and write. So K minus WL. So this is, so here when we were writing the equations earlier, uh, what was form of the equation? Just a slight divergence from what we were discussing. This is what we were discussing earlier, that you have a equation of the form mu double dot plus ku plus cu dot is equal to pt. Now, if this is a free vibration problem, we know no external forces acting on the system. And let's say in this question, which we just discussed, we did not have any damage. So this was also zero. So, sorry, this term is synonymous with this first term, and this term is synonymous with this second. So what do you see in this question? That uh, this is the effective stiffness, or K minus WL is the effective stiffness of the system. What will happen when K is equal to WL? Any guesses?
No stiffness. So
Yes. No stiffness means this body cannot have this motion. That is, we say that the system becomes uh, unstable under its own weight. That is,
okay, so
it will, yeah.
like a thread,
Sorry, what did you tell?
like a
Like
thread,
I did not get you.
thread.
Right. Like a thread, the stiffness goes to zero. Right. It will it will become unstable, or you can tell that uh, the it will buckle under its own weight. So, what is the critical value of uh, W that this will happen when
W.
it uh,
Okay.
W critical, or this term in the bracket K minus WL goes to zero, when W will be equal to K by L. So, this is the critical weight of the weight, so that the system becomes unstable. Why it is becoming unstable? Because the stiffness is going to zero. So at this weight, effective stiffness is equal to zero, and system becomes unstable under its own weight. Sorry. Any doubt in this question? Okay, I assume it's clear. So let's do one more question. So I'm heavily relying on the book Dynamics of Structures by A.K. Chopra. I find it mm, very easy to follow, and I'm discussing, I'm picking up questions from there. So you might also uh, find this book, like you can download a copy of this book, or you can buy its copy. It's a very good book. In this question, suppose I have a cantilever beam, and from its tip I'm hanging a load, and let's say I'm applying a force P of T. This the weight is W, and this K is equal to 20 pounds per inch. This length is 10 feet. This is equal to 2 inch diameter. And I want you to derive the equation of motion of the weight W suspended from a spring at the free end of a cantilever beam. And you should neglect the mass of the, like, for the time being, just consider, you don't need to plug in values. First, let's uh, set up the equation in terms of the variables, and then we'll discuss what we can do with this question. And yeah, that is the question. You have to write down the equation of motion of the weight W. Derive equation of motion of weight W under the force P of T. Okay. Uh, I want you to try it for a few minutes, and then we'll discuss. Let's say I give you 2 minutes. Think properly. Here, the hint is, we think about the statics of the problem. The beam is clamped at this end. When you apply a tip load, it will undergo a static deflection, and you will have the dynamic part. Uh, Static deflection is due to the weight of the body, like that. That is what I meant by static deflection. So basically, there are two forces. One is the weight, which is not changing with time, and the other is the force P of T, which is changing with time. So you will have two kind of displacements in the vertical direction. One due to the weight W, which is not changing, and due to the force P of T, which is changing. Think about that and try to solve this question.
Ma'am, the cantilever is rigid.
No, it can deform.
Okay, so like PL cube by 3 deflection, it will be there.
Yeah, it will be there. Or for the time being, you can consider the only flexural stiffness present in the system is due to K. Let's simplify this. We can also always bring the stiffness of the beam into picture later on. So let's
Okay.
simplify it for the time being.
Okay. Ma'am, is the free body diagram correct?
You can share your screen. Just hang on for a second. Yeah, you may share your screen.
Ma'am, could you see my video because I'm writing on a notebook?
Uh, just, yeah, you can share your video.
It is already on. Can you see?
No, no,
Um,
start visible. Okay, let's discuss the question. And if you have any follow-ups, you can always write down a mail to me. I'm very active there. So if you
okay.
have something which you want to discuss in person,
Okay.
yeah. So first thing is this is my initial configuration. Let's say now, let's say the beam has to have flexural um, deformation. Otherwise, I think so. I just misguided you. I just realized now. So, if there will be no flexural deformation, no flexural stiffness, then because of this weight W, there won't be any deflection. So, my entire point of giving this question will get defeated. So, in that context, let's assume that the beam is rigid. Then, if the beam is rigid, that flexurally rigid, it would not bend only because that is under the weight W, there won't be any deflection. Only because of the spring force, there this spring will uh, that the static deflection due to the weight will not be there. The spring will just extend itself. The weight would go down and the forces acting on the block would be because of the weight there won't be any deflection, and you have this P of E, K of U, and this inertial force M U double dot, and you can write it down, but my motive was something else. What I wanted to showcase is, if this is the body, the beam is uh, deforming, and the spring is also extending, and this is my mass, and I am measuring my U, let's say I'm calling it U bar, that is the deformation from the undeformed position. So This blue line is the undeformed position, and this is the deformed position, right? So if I want to write down the free body diagram, I'm drawing the free body diagram. So what are the forces? You will have the spring force Fs. You will have the this external force P of T. You will have the weight W, and you will have the inertial forces Mu double dot. And if I write down the equilibrium equation in the vertical direction, it will be Mu double dot plus Fs is equal to W plus P of T. And uh, if I just rearrange it, I can write it as Mu double dot plus Fs. Uh, okay, let's not rearrange it at this stage. Okay, now uh, what is this U bar made up of? This U bar, like what does it consists of? U bar has some static portion and some dynamic portion, where UST, or let's UST is the static displacement due to the weight W, and U is measured from this position of equilibrium. So if I draw it here, so because of this weight, let's say the body is not visible. Because of this weight, the body will come down a little bit. So this position is UST and this is U. This you can say that this is the position of static equilibrium. And what is this UST? Can someone tell me what is this UST? What, like, how will I write down UST? Because this is the deflection because of the weight W. So if the system, let's say the equivalent stiffness of the system is KE, we'll figure out what KE as well. There in KE, you will have participation of this spring stiffness uh, K, and you will have the participation of the beam as well. So,
W by KE would be UST.
yeah, right. So, Fs is Ke into U bar. This is one thing which I'll try to find out. Now I want to find UST. UST, as you rightly told, it will be W under this weight and divided by stiffness. This is the value of uh, UST. Now, uh, so this is figured out, and now what do I do? So this I had done wrong. Nobody pointed this out. So when we write acceleration, it's always in terms of the total acceleration, or it will be with respect to this total variable U bar, right? This was not correct. And when we write down spring force, let's say, let's take that example. Suppose in each you have a spring like this, and you pull it by a certain amount, let's say delta x. What is the force in the spring? It will be the spring stiffness K into delta x. That is the change in the length of the spring because of application because of the application of the force. Basically what I want to highlight, that force is equal to stiffness into the change in the length, or the relative it should be told as the relative deformation. So the Fs, the spring force, will be K into U, not U bar. So I highlight these 2 points here. Now just substitute here that M, what is U double dot? U double dot will be U. Am I doing the right thing? Yeah, I'm doing the right thing.
When we are seeing UST,
Hmm.
there as well there is participation of spring, correct?
No, it is only due to the weight. Yeah, so you mean the stiffness participating uh, is due to beam as well as the spring? Yes, yes. Yeah, is that what you were asking?
Yes, ma'am.
Yes.
Okay.
So just substitute these terms back into the equation, and so I have U bar is equal to U plus UST. Keep in mind UST is a constant. So U bar dot is U dot. UST is a constant, so it goes away. U bar double dot is U double dot. Fine. And so I can substitute that M U bar double dot becomes U double dot. Fs is Ke into U. Now W can be written as, I am missing something, I feel here. Now this weight W will come into picture, fine. And we will have PT. Yeah, I just figured out. So earlier, when I'm writing this force Fs, it was with respect to the undeformed configuration. So it will be with respect to U bar. So here you will have U bar, which can be written as U plus UST is equal to W plus PT. So if I write this down, so KE into U plus KE into UST is equal to W plus, now W is equal to UST into K. So this and this goes away. So with respect to this light blue line, that is the static equilibrium line, your equation of motion is mu double dot plus Ke times U is equal to P of T. So the point which I wanted to demonstrate with this is, if you write down your equation of motion with respect to the static equilibrium line, that is after considering UST separately, that is the deflection which is happening due to the weight, then uh, you don't need to consider weight in your equation, because that just cancels. And one more question was there: how do you calculate AE? How is it established? So Fs is equal to Ke into U bar, right? Now, what is U bar? U bar is has um, deflection from the U plus UST. So, what I want you to write is, so U bar consists of deflection from spring plus deflection from beam, right? Now this Fs force will be, you will have stiffness of the beam as well as the stiffness of the spring. So this force will be K into delta spring, and it is also equal to K beam into delta beam, right? So what is the total deformation? You can just use this equation. So U bar can be written as Fs by Ke. I'm using this equation. Delta spring can be written as Fs by K, and delta beam can be written as Fs by K beam, because this system is in deflections are getting added. That is, it's in uh, series. So from here you can figure out what is the value of Ke. You can substitute. I'll just write down the expression directly. Ke is equal to K into K beam by A plus K beam. And what is the stiffness of the beam under a point load? We know that a cantilever beam subjected to a point load, this stiffness delta is PL cube by 3EI, or in other words, stiffness is 3EI by L cube. In uh, so from here, this is nothing but K beam in this scenario is 3EI by L cube. And if you know the stiffness of the spring, like you know it here, you can just substitute it in this problem and calculate the value of Ke. So it gives you a sense of the effective stiffness of the system. So
Ma'am, what is Fs in the expression?
this is the force generated, this Fs.
Force due to?
The force due to uh, stiffness of the spring and the beam. You can call it the resisting force.
And because that force is constant, means it is passing through spring as well as beam, it is constant. So we are using Fs by K and Fs by K of beam.
No, yeah, you can think it in that manner also, but first think like this. What is the total deflection? U bar, what is total? You will have certain deflection which is happening because of the spring, because the spring is deforming, and because the beam is deforming in the transverse direction. So is this equation clear for U bar?
Yes, ma'am. U bar is clear.
So this tells that this system is in series. If something
Correct.
is in series, the force will be the same. So the system is something like that. You have a spring K1 and you have a spring K2, and you are pulling it with a force P. So the forces in the spring will be same. If the deflection in the spring is delta 1 and delta 2, so total delta is delta 1 plus delta 2, and force in spring 1 is equal to force in spring 2 is equal to P. This is exactly what I'm doing. Just like the how we visualize the spring is slightly different in this question. Otherwise, we are doing exactly the same thing.
Yes, ma'am. Got it.
Yeah. Okay. Okay. I sorry I am missed this equation a bit. Then let's see. Could you follow the derivations which were done in the class for the free vibration? How the derivation was done? Uh, like how was, like if the system is uh, under free vibration, how the equation of U was written. Was that clear? Any any thoughts on that, or any area which you want me to highlight?
Ma'am, actually, I haven't seen the third and fourth videos. So, if you
Fine, fine.
could.
Yeah, the third and I believe it's related to free vibration only. Initially, ma'am talked about undamped vibration, and later on she talked about damped vibration. So, undamped meaning basically there is no energy dissipating source. It's purely for academic purposes, when there is no damping in the picture, and basically the system goes on vibrating forever, but that will never happen. This is when she talks about undamped case, which is it's the starting point from where we start, and then we move on to a damped case where damping comes into picture. Okay, this we can study. In damping we have three kinds of cases: over damped, under damped, and critical. And then let's write down the equation. So let's do that. So it will be good that if we start from the undamped case. Just hang on for a second. So let's look at undamped free vibration. Let's like it's a good idea to go through the derivation as well, and then we'll go for the damped free vibration as well, and there we'll look at the concept of underdamped, overdamped, critical. Where is this scenario seen um, in real life, and uh, in structures, in civil engineering structures we mostly encounter underdamped systems. So I'll explain you that as well, why do we encounter that more. So starting with this undamped free vibration. So we just saw that, let's consider a spring mass damper system which we were discussing. So for the time being, we have no damping in the system. This is my mass M. So this is the system, fine. And you are not applying any force on the system. Like if you have a force P of T, the spring stiffness is K. What will be the equation of motion? I'm directly writing this down. And suppose your variable is X. So it will be Mx double dot plus Kx is equal to K of T. Now, let's say it's a free vibration problem. That is, P of t goes to 0. So, to set it into motion, you have to give some initial condition. Initial condition can be in terms of initial displacement and initial velocity, or one of them. So, you need to have something, you need to do something to set it into motion, right? So, you have, so the initial, I missed an I, initial condition can be in terms of displacement or velocity, x0 or x dot 0. Fine. Now, how do I solve this? So I have to solve the equation mx double dot plus kx is equal to 0. So what you can tell about this differential equation? One thing, it is second order, x double dot is appearing, then it is linear, and
Yes.
it's a homogeneous differential equation. Right side is 0 and the coefficients are constants. These are the things which you observe in this differential equation.
Yes.
Okay. Now, the solution will be of the form we know for this type of differential equation. Let's say it has a solution of the form x is equal to e power s. Now, this is solution which you are suggesting. Here you don't know what is s. So let's substitute the solution back into the differential equation. How we classically solve differential equations? So here we can write that x dot is s e to the power st, x double dot is s square e to the power st. Just substitute it back. So m x double dot is s square e to the power st plus k x is e to the power st is equal to 0. So here I can write m s square plus k. I take e to the power st common is equal to 0. Now here either e to the power st is 0 or the term which is there in the brackets, it is equal to 0. If e to the power st is equal to 0, means my solution x is 0, but we want to get a solution. So for that, m s square plus k is equal to 0 because e to the power st can't be equal to 0. Now, from here we get S1 and S2 will have the form K by M under root, and you will have an I term as well because S square is equal to minus K by M under root of minus 1 is iota. Fine.
Yes.
Now let's write under root of K by M is equal to omega n, which is later on you'll see this is the natural frequency. You have undamped natural frequency. This is an undamped case, so undamped natural frequency. You have damped natural frequency. We'll see that later on. Now, so we see e to the power s1t and e to the power s2t. These are two solutions of the differential equation, also known as the two bases of the differential equations. And how can we write down the general solution? We can write down the general solution like this. X of t is equal to, you have a coefficient a1 e to the power s1t plus a2 e to the power S2t. What is S1? So with this thing, I can write plus minus. This is what I'm assuming. So from here, I can tell S1 and S2 is plus minus I omega n. This is what I'm substituting in this equation, that A1 e to the power I omega n t, A2 e to the power minus I omega n t. Okay. Now this A1 and A2, that is these coefficients, they can be calculated using uh, the initial conditions in problem. So I'll pick up a case and do that as well. Okay, before that, e to the power I omega nt, basically instead of exponential, I want to write it in the form of uh, cos and sine and coses. So for that, I'll use the Euler's equation. So e to the power omega n t can be written as cos of omega n t plus I sine of omega n t because I want to get rid of exponential. E to the power minus I omega n t is cos omega n t minus I sine of omega n t. Just substitute it back here. So x of t is a1. This is cos of omega n t plus I sine of omega n t plus a2 cos of omega n t minus I sine of omega n t. Now let's collect the cos omega n t term. So you will have a1 plus a2, right? And let's collect sine omega n t term. So you will have I times a1 minus I times a2. Now let's write this as a and this as b. So you have the solution a cos of omega n t plus b sine of omega n t. Now you can calculate a and b using initial condition. Let's say your initial conditions are at that these are your initial condition. That is, if I put t is equal to 0, this is equal to, like, at t is equal to 0, your displacement is x of 0. So uh, sine 0 is 0, cos 0 is 1. So a is nothing but x0. And then you have to use this, the second condition, x dot 0. So let's write down the expression for x dot t. It will be a omega n differentiation of cos omega n t is minus sine omega n t into omega n, and b omega n into cos of omega n t. Okay. Now I want to use the other fact that uh, x dot, the velocity when the velocity at time t is equal to 0 is x dot 0. So x dot 0 is the velocity. This term goes away because at time t is equal to 0, sine 0 is 0, and we have b omega n. So what is b? B is equal to x dot 0 by omega n. So using initial conditions, we found out the value of a and b, right? So now you can write down what is the expression for x of t. A is x0, b is x dot 0 by omega n. Sorry, cos of omega n t. B is x dot 0 by omega n sine of omega n t. So this is the expression for x, right? Now let's do it for a damped case, right?
And in this derivation, if we do not start from the mean position, then the condition that at time equal to 0, the velocity is 0 would change and the expression would change, correct?
What do you mean by mean position?
Uh, in a simple spring system,
Mhm.
when we are starting, so on the mean position, the velocity is 0, correct?
Mhm. You
So
no,
that is,
okay. You are thinking about uh, just people are coming now. Uh, hmm. So this is what I'm talking about. It does not matter uh, from the position. So uh, let's say you are thinking that okay, you pull the block to a certain distance here, let's say by a certain amount x, so that becomes your value for x of 0, and at that point if you leave it, the velocity x dot 0 will be 0. That is one
yes, ma'am.
case. That is one case. But let's say at this position, you don't provide any uh, x, any deformation. You just provide a certain velocity
Okay.
by just impart some, let's say hypothetically, I don't uh, deform it, I just give it a velocity. So that won't be the main position, that would be at this position itself if I can impart a velocity.
Okay. So you are saying something like dv velocity is given.
Kind of,
Uh,
kind of,
okay.
yeah, kind of. Somehow you set the body into the velocity. Like currently, I'm not able to give you any physical example. Uh, like I would think about it, but here setting up the body into mean from the mean position is not a necessary condition. It just depends how you handle the initial values, uh, the initial conditions. So I
Okay.
think so. I could not explain it. I'll try to like think about that, and maybe I can give you a more physical explanation in the next class. I'll try
Okay,
to
ma'am.
do it. Okay.
Thank you.
Yeah. So, okay. This is done. Okay. 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 Now let's talk about the damp free vibration.
Ma'am, what do we mean by free vibration?
Free vibration is when no force is acting on the system.
Okay. No external forces
No
applied.
external forces acting in the system. So how, why is it moving? It is because of the initial conditions. That is why in
Okay.
this solution there is no external force. What is appearing is this x0 and x dot 0. These are the initial conditions which are coming into your solution. You can
Yes.
think of it like, uh, suppose you have a cantilever.
Mm-hmm.
You pull it with a string. Suppose you have a cantilever. Somehow in the lab you take a cantilever and you tie the tip with a thread with some support. Suppose you have a support here, and then you pull this string with certain mechanism. You just pull the string and then you cut the string. What
Okay.
will happen? It will, from this side it will go this side, then again it will move this side, and slowly it will come to its initial position. This
Yes.
is this is free vibration.
Okay. But if it would not have come to the mean position, then that would be undamped. And this is
Yeah,
damped.
damn. Like
Okay.
this is like I was giving you a physical situation. It will always come. So this is what free vibration is. No force is acting on the system. The entire it is set into motion only because of the initial condition.
Okay, ma'am.
Okay. 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 So I'll just plug in my charger. Okay. So let's do damp free vibration, and in damping for academic purposes, we always consider it to be viscously damped. And how is the viscous force defined? It is C into the velocity. This is how we handle. Like, see, damping is anything which leads to loss of the energy of the system. Now, let's say when a certain body is moving in the air will provide resistance. So, because of that, energy will be lost. So, this air resistance is also a source of damping. Then, let's say you have mm, let's say you have a concrete, this a concrete beam kind of thing. While moving, it can happen that cracks can form. Concrete will come when concrete comes in tension, cracking will happen. Because of the crack formation, damping energy can be lost, and that is also a source of damping. So there can be various sources of damping, but when we want to treat it mathematically, uh, like viscous damping is a, it's a convenient manner, and this is how we study damping, uh, like when we want to do it academically. Or if there is some other form also of damping as well, we like to convert it into viscous damping and study. So maybe this will be covered later on, how do we convert it, or in the next class I can touch upon that as well. Okay, so we have viscously damped free vibration. So here the equation of motion will be, I'm not drawing the spring mass damper system again. Okay, since I'm starting a new topic, just let's go ahead. You have a spring, you have a damper, spring stiffness of is K, damper coefficient is C, this is mass, this is X, free vibration, no external forces acting. So mx dot plus cx, mx double dot plus cx dot plus kx is equal to 0. So let's write it down in this equation. X dot is c by m. I'm just dividing the equation throughout by m, plus k by m. X is equal to 0. So we had just written in the previous page that omega n is k by m. So omega n square is equal to k by m. Okay. Now we define a term, that is the critical damping coefficient CCR. C critical damping coefficient is equal to C critical. It is equal to 2 omega n into m. So, and we introduce one more term, that is the damping ratio, which is zeta is equal to, sorry, zeta is equal to, just hang on a second. Zeta is C by C critical. This is one more term. These are just introduced to make, so that you can handle the equation easily. C critical is 2 omega n into m. So what is C by m is equal to 2 zeta omega n. So substitute this and this in the in this equation. Let me call it equation 1. So substituting in equation 1, you have x double dot c by m is 2 zeta omega n x dot, k by m is omega n square into x is equal to 0. Fine. Now, this zeta, when it is equal to 1, means damping is equal to critical damping. So, so damping can be of three types. It can be critical when zeta is equal to 1. It can be under damping or over damping. So under damping is zeta is less than 1. Over damping is zeta greater than 1. So what do we mean by that? Just very sorry. So zeta is less than 1 means we can say C by C critical less than 1. So the damping in your system is less than critical damping. This is when C by C critical is greater than 1. So when C is greater than critical damping. So what do I mean by this? So when your damping is more than critical damping, let's see how do I explain this. So let's solve this equation. Then this thing will be clear. So x double dot plus 2 zeta omega n x dot plus omega n square x is equal to 0. So here again solution is of the form 2 to the power e to the power st. Now let's substitute it here. Here again x dot is s e to the power st, x double dot is s square e to the power st. Substitute these terms in this equation which I just derived. So s square e to the power st 2 zeta omega n x dot is s e to the power st plus omega n square x is e to the power st is equal to 0. So let's take e to the power st common. S square plus 2 zeta omega n s plus omega n square is equal to 0. So again with the same explanation, e to the power st can't be equal to 0. So the term in the bracket has to be equal to 0. So s square plus 2 zeta omega n s plus omega n square is equal to 0. So from here, let's consider that the system is overdamped. That is zeta is greater than 1. Since it is a quadratic equation, you can directly write down the roots. It will be minus 2 zeta omega n minus b plus minus under root of b square minus 4 ac by 2 a0. So if I can write this in the form minus zeta omega n plus minus omega n zeta square minus 1. This I can write, or let's take omega n common, minus zeta plus minus under root of zeta square minus 1. So it's real, and if zeta is greater than 1, here zeta is greater than 1, what will be my general solution? General solution will be x of t will be a1 e to the power s1 t plus a2 e to the power s2 t. Just substitute the value of s1 and s2. So a1 s e to the power s1 will be minus omega n. I am taking minus common. Okay. Let's go theta. Okay. Let's consider one with the plus sign. So minus under root of zeta square minus 1 into t. And again with a2. Again, if I take minus common, Now let's do it with the plus sign. So plus under root of zeta square minus 1 into t. So what we see is that if zeta is greater than 1, let's consider zeta is 2. If zeta is 2, then yeah, I just lost connection briefly. Am I audible?
Yes, you're audible now.
Yeah. So if zeta is greater than 1, both these terms, so if zeta is positive, these terms in the exponent, like these terms would be positive. This term as well as, where did my e go? These terms, if you try plotting these terms for a positive value, you will see a positive value of zeta. You will see that this term is positive as well as this term is positive, and it's a exponentially decaying term. But you will find that it does not undergo any oscillation. It will just uh, if with time, if I plot x of t, it will just go down like this without any oscillation. So there are no vibrations. And where do you commonly see this in life? You see this in the door. At the top of the door, you have certain kind of door closers. So there, you don't want the door to. Suppose you put pushed the door and you went out. You don't want to oscillate it, and and it might hit someone. So you just want it to slowly come back to its main position. And this is what happens when the system is overdamped. Suppose the system is underdamped, then what do we see? Or let's say if the system is critically damped. If the system is critically damped, the solution remains the same. That is,
Would again be positive.
yeah, if zeta is 1, you will the only solution which you will get is s is minus omega n. So what will be the general solution? X of t will be something like a1 plus a2t. So this is how classically solutions are written when the roots are equal. It is written like a1 e to the power st plus a2 into t into e to the power st. So if you refer to any book on differential equation and check if the roots are equal, this is how things are written. So a1 plus a2t e to the power s of t, just substitute a1 plus a2t, s is minus omega n t. Uh, so we can see the plot is something. This also goes to 0, but it has like, let me draw it with the red term. It will be something like this. It will just drop and then it will go to 0. So this is the case of critical damping. And what is interesting is the next one, where the solution is underdamped, that is zeta is less than 1. If zeta is less than 1, then what happens is uh,
Will have imaginary part as well.
so, so, so what will be the expression for S1 and S2? It will be omega n, then you will have minus zeta plus minus. So the zeta square minus 1, this will be imaginary. So, it will have a minus 1 under root. So I take it out. and I flip this inside 1 minus zeta square, and the roots will be as complex conjugates. So what will the general solution be? X of t will be, again, you write it as a1 e to the power s1t plus a2 e to the power s2t. Substitute these values of s1 and s2. So, so you will have a1 e to the power s1 is omega n minus zeta. Let's consider plus I e to the power minus zeta square into t plus a2 e to the power omega n minus zeta minus I under root of minus this n t. Now, uh, I can, this first term can be written as a1, it is there, sorry, e to the power minus omega n t multiplied by e. So, e to the power a plus b is e to the power e to the power a into e to the power b. So we know about this property, so I'm using it here. What I'm doing is I'm writing e to the power omega n. I'm substituting, separating this term, e to the power I omega n under root of 1 minus zeta square into t plus a2 e to the power minus omega n zeta t e to the power minus I under root of 1 minus zeta square omega n t. Then what I can do, I can take e to the power minus omega n zeta t to be common. I am left with a1 e to the power I omega n under root of 1 minus zeta square into t plus a2 into e to the power minus I omega n under root of minus 1 minus zeta square into t. Now, omega n under root of 1 minus zeta square is written as omega d. This is the damped natural frequency, omega d. So let's use it here. So x of t is e to the power minus omega n zeta t a1 e to the power I omega tt plus a2 e to the power minus I omega dt. So what you see, this part in the bracket is similar to what we got here, a cos of omega nt plus b sine of omega nt. The difference here omega n is coming into picture, and here omega d, the damped natural frequency, is coming into picture. So we can just extrapolate the form of the solution here. Like we started with a solution of this form, and we told that this can also be written as a cos of a cos omega nt plus b sine of omega nt. So let's use this fact here. So e minus omega n zeta t, this is a cos of omega dt and b sine of omega dt. How will you find a and b? Again, you will use initial conditions to do the same. So a and b are calculated using initial condition. So this is the uh, okay. Now, and if I plot it here, it is seen that See, I'm doing it in a very schematic sense. In a very schematic sense, it will come down and it will oscillate and it will come back to this position. So it will show oscillation. So is this light blue is zeta less than 1, dark blue is zeta greater than 1, and this is when damping critical zeta is equal to 1. Okay. So
Could
yeah,
you tell the reason of substituting cos and sine in E?
there is no such reason. It's what I feel it's easier to visualize it because we are more comfortable with sine and cos. Otherwise, I can't think of any reason why do we go into uh, because it's the same thing. Whether you do it in exponential terms or sine cos, it hardly matters. So I think I ran out of time today. I'll try to better plan the lectures from next day. So any doubts in today's session and any inputs from you, whether I should focus more on problem solving, more on concepts, or a mixture, what we followed today. Today we did kind of a mixture. We did some question also. Then I tried to do the derivation as well because we have a habit of looking at derivations and thinking, okay, we understand it. When you write it down, put all the terms because in the books they'll skip some steps and do. So I tried to do the derivation so that things become clear, like how you're basically manipulating the equation. So any comments on how should I include more questions or uh, do you want the pace to be a bit faster or slower?
Today's lecture was very good.
Okay, then let's continue like this. And if you have any doubts in this first part, in the first week lecture, you can always email to me. This is my email ID. I hope this lecture will also be available on the NPTEL site. They might put the link there. And yeah, that's all. And if you, while reading second week's material, if you find something which you can't follow, you can explain, you can inform that topic to me via email so that we can take up in the next class. I'll be better, like if you tell me the topic, I'll be better prepared so that we can take up that material and we can discuss.
And
And
ma'am, one thing,
mhm.
what is the format of exam? Uh, what is the
uh,
proportion of theoretical and problem based question?
I believe it will be an MCQ kind of thing, but commenting on the proportion of theory and this is something which I don't know uh, the weightage. So, but it will be MCQ. So concepts will be there. Some numerical will also be there. So,
Okay,
or you can write
so
that
all
question
questions.
in the forum.
Okay,
Yeah, yeah.
so
You
in
can.
main exam, all questions will be MCQ,
Yeah,
MCQ based.
as far as I know, it is MCQ based. You can always like these are kind of logistic questions which you can directly ask in the NPTEL course. So so basically, I am a PMRF fellow and uh, I am a teaching assistant for this course. So all
Yes,
these
yes.
examination things will be handled by the NPTEL team. So they would be better to answer these questions. I'm only here to help you understand this topic in a better way, and in this process clear my concepts and doubts as well. The more and more you ask, it will help me in improving my concepts as well. So I am here only for uh,
Okay.
that
Okay.
purpose. Yeah,
Okay.
yeah.
Definitely. Okay. Okay.
Okay.
Okay, ma'am. Thank you.
Okay, okay. Thank you for attending the session. So, happy Saturday. So, let's again meet next Saturday at 6 o'clock. And if you have any doubts, please mail it.
So, ma'am, there is one more class on 25th, I think.
Yeah, so that is one more TA. So, he'll be also doing a similar kind of thing. And I will be conducting classes every Saturday. He'll be doing it on Tuesday, I guess, Tuesday or Wednesday. So this is the arrangement. But topics covered will be the same. It's not like he will do a certain portion, I will do a certain portion. We'll be
Okay.
both taking up the entire portion. The perspective of the topic would be might be different for him and me. Suppose I understand a certain thing in a certain manner, so it's good to attend both the session if possible. Otherwise, you
Okay.
can always go through the recording. It will be available.
Okay, ma'am. Okay.
Okay,
Thank you.
okay, okay, okay. Okay, thank you for attending the session.
Thank you. Thank you.
If there are any more questions, anything, uh, you can say, or you can leave. Uh,
Okay, ma'am. Thank you. So, we'll meet in
okay,
next session.
okay, okay, okay. I'll close the meeting. Thank you, everyone.
Thank you, ma'am.